Hello, welcome back to the wonderful world of astronomy. We are in chapter 17 titled Star Stuff. In chapter 17, you are going to learn about the life of a star. And this part 1 video will look at the life of a low mass star. First, we need to do a review to make sure you understand concepts learned in chapter 15. So let's look at this table of stars. Here we have a few stars by name. In this column, the second column, we have the apparent magnitude, and then the spectral type, and then the luminosity class. You learned all these things back in chapter 15. So looking at this table, which star has the highest surface temperature? So you might want to pause it for a minute and think about it. As you think about the surface temperature, remember that's related to the spectral type, and remember the spectral types O, B, A, F, G, K, M. So we look for O stars, and there are none. We look for B stars. We see a B1 and a B7. Then we remember that the subtype 1, that's going to be hotter than 7, so the highest surface temperature is Spica. The next question, which star has the lowest surface temperature? Well, the spectral types O, B, A, F, G, K, M. So we look at M, and there's an M1. There aren't any other M stars, and so Antares is the star with the lowest surface temperature. Which star looks the brightest in our sky? When we think about what looks the brightest, we're going to look at apparent magnitude. And remember, the smaller the number, the brighter it is. And so here we see a 0. We look for, is there anything brighter than that? Any negatives? Here's a negative 0.7. Here's a negative 1.4 Sirius. And Sirius actually is the brightest star in our sky, aside from the sun. The next question, which star looks the dimmest in our sky? We'll look at apparent magnitude, look for the largest number. I see a 1.4 positive. That looks like the largest numbers. That's going to be the dimmest star, Regulus. Which stars are finished fusing hydrogen into helium in their cores? I want you to remember that that is the definition of a main sequence star. A main sequence star is currently fusing hydrogen into helium in its core. And so when it's done fusing hydrogen to helium, it becomes something else, a giant, a supergiant, eventually maybe a white dwarf, but it'll be something other than main sequence. So we're going to look in the luminosity classes. And here we see the last 4 on this table are 5s. Those are main sequence stars. And the 4 above it are non-main sequence. Here we have Aldebaran is 3, which is a giant. Alpha Centauri A, well, that's a 5 also, so that's main sequence. Antares is 1. Canopus is 2. So we're going to go with Aldebaran, Antares, and Canopus. Which star is most like our sun? There might be a few variables involved with that. We're not going to worry about the apparent magnitude at all because that just has to do with how far away it is from us. But we'll think about spectral type and luminosity class. Remember that our sun is a G2 class 5 star, G2 main sequence star. So we're going to look for something on this table that is close to a G2 5. And there's one spot on. Alpha Centauri A is a G2 main sequence star. Which main sequence star has the highest mass? If you remember, on the main sequence, starting at the upper left hand, the O and the B stars, those are the most massive stars. So actually the farthest up on the main sequence it is, the more massive. So we're going to look for no O stars. Here's some B stars. B1 beats out B7. So the most massive is Spica. Which main sequence star has the longest lifetime? Longest lifetime on the main sequence is going to be the one that's farthest down and to the right. So we'll look for M stars. Now, you can see this M star Antares, but it's not a main sequence star. The question says, which main sequence star has the longest lifetime? When we talk about the lifetime of a star, we're usually talking about the main sequence lifetime. So we're going to not even think about Aldebaran, which is class 3, Antares class 1, and Canopus class 2 of the main sequence stars. Here we have a G2, that looks promising. All the others are A's and B's, and so G is going to be the farthest down and to the right, so Alpha Centauri A. I want you to remember, this comes from chapter 14 when you were first learning about the sun, that the sun, as well as every star, has a competition of forces. Forces pulling it in, crushing it in, and forces pushing out. And in the case of crushing it in, you can see the green arrows. It is gravity pulling it in. And in order for it to be in equilibrium, there has to be something pushing out against gravity. It's some kind of pressure. Now, when you were learning about the sun, you learned that it's the radiation, the energy that's formed inside the core causes this pressure pushing out against gravity. So our sun is in equilibrium. When we learn about the life cycles of stars in chapter 17, you're going to see that often in the life of a star, it gets to a point where the nuclear fusion reactor, that core, will shut down. It might only be a brief shutdown, but it will sometimes shut down. And then there's no more red arrows for the moment in this picture. And so gravity will crush the star in, heating up the core, and then igniting more nuclear fusion so that it comes back into equilibrium. So just keep this concept in mind as you go through the life cycle of stars in this chapter, that there's got to be something pushing out against gravity. And if there isn't anything pushing out against gravity, then the star's just going to crush down to zero size. Let's now look at how a star's mass affects nuclear fusion. There below you see the Hertzsprung-Russell diagram. By now you should be very familiar with the details of such a diagram. The mass of a main sequence star determines its core pressure and its temperature. So up here to the left, these high mass, high luminosity, high temperature stars. Stars of higher mass have a higher core temperature and more rapid fusion, making those stars both more luminous and shorter lived. You learned about that in chapter 15. Stars of lower mass, down and to the right, have cooler cores and slower fusion rates, giving them smaller luminosities and longer lifetimes. We divide stars up into different categories based on what will happen during their lifetimes. So I want you to learn these categories. The high mass stars, those are stars, we're going to define that category as stars with greater than 8 solar masses. So on the Hertzsprung-Russell diagram, it's everything from about here up and to the left. Intermediate mass stars are between 2 and 8 solar masses, so these white to blue stars right in there. Low mass stars are going to be everything less than 2 solar masses. So all these, and that would include the sun. And then, not a category of stars, but I'll throw it in anyway, brown dwarfs are these failed stars, almost stars, but not quite, that are less than 0.08 solar masses. And you learned in chapter 16 how if they don't have that much mass, then they will not be able to sustain nuclear fusion in order to be a star. All right, so at this chart, I want you to remember low mass stars are less than 2 solar masses, intermediate mass stars are between 2 and 8, and high mass stars are greater than 8 solar masses. And how much their mass has is going to determine what their life is going to look like. Remember also from chapter 16, the breakdown of masses of newborn stars. Between 0.08 and 0.5 masses, about 77% of stars have that much. From 0.5 to 2, about 19%. Now this dividing line right in the middle of the page where I'm pointing, is stars less than 2 solar masses. You just saw on the previous screen that that is low mass stars. So 77% plus 19% is about 96%. And so I want you to understand, as I talk in this video about the life of low mass stars, this is 96% of stars. The far majority of stars are going to follow the life of what I'm going to describe in this video. In the next video, I'll show you intermediate and high mass stars, and I want you to understand that those are just a small minority of all stars. As we study the life as a low mass star, goals for learning: what are the life stages of a low mass star, and how does a low mass star die? Life stages of a low mass star. A star remains on the main sequence as long as it can fuse hydrogen into helium in its core. Once all the hydrogen in the core has been converted to helium, the core is going to shrink and it will heat up. So at that point, there momentarily is not going to be any nuclear fusion. If you think about the core of a star as the nuclear reactor, once all the hydrogen is converted into helium, there's no more fuel, and so the reactor shuts off. Gravity is going to crush down on the core and shrink it. Observations of star clusters show that a star becomes larger and redder and more luminous after its time on the main sequence is over. Here's what happens inside a red giant. So this is the star after it leaves the main sequence, and why it grows larger. A minute ago, I said that there's no more nuclear fusion, at least temporarily, and the gravity crushes down on the core, implying that the star is going to shrink. So why does it get bigger? As the core contracts, hydrogen begins fusing to helium in a shell around the core. Let's look at this picture. When it was a main sequence star, like our sun is now, you have this red ball represents the hydrogen fusing into helium. The yellow around it and the orange around that and the orange-red around that are just all hydrogen with no fusing. So that is a main sequence star. Now, once all that hydrogen gets used up, let's go down to this picture of a star expanding into a red giant. You have the contracting inert helium core. Inert just means it is not fusing, so it's a ball of helium. However, around it is very high temperature, high pressure hydrogen. So this shell that surrounds it, this fuses into helium. So the nuclear reactor has started up again. That hydrogen shell that is fusing into helium is first of all going to crush down on the helium core, but it's also going to push outward and make the star much larger. As the star expands, its surface cools off, and so it becomes red. So it's a red giant. Now, eventually you can get to a point where there is helium fusing into carbon. Helium fusion does not begin right away because it requires higher temperatures, about 100 million Kelvin, than hydrogen fusion. Remember, hydrogen fusion only requires 10 million Kelvin. And it requires a larger temperature, a higher temperature to fuse helium into carbon because there's a larger repulsive force between those 3 helium nuclei. And so it just takes a lot more to ram them together. You can see in the picture up above, it's just showing 3 helium nuclei becoming 1 carbon nucleus plus energy. Fusion of 2 helium nuclei does not work, so helium fusion must combine 3 helium nuclei to make carbon. Now, there's a bit more complication to it than what I said in the last screen, that fusion of 2 helium nuclei does not work. It sort of works. Let me show you this. It's actually what's called the triple alpha process. And it's just broken down into more detail what I showed on the previous screen. Here's really what happens. 2 helium nuclei come together. And in the process, they give off gamma rays, so that's energy. and it becomes beryllium-8. However, beryllium-8 is very unstable. It is prone to falling apart. However, in the temporary state in which it is beryllium-8, if another helium-4 comes into it, then it will fuse to make carbon-12. But this is just the details of it. All you really need to know for this class is that 3 heliums have come together to make a carbon. And so this is what's going on in this next stage of the star. Remember, when I showed you previously a diagram like this, it was an inert helium core. Well, now there is helium core fusion. So you've got double fusion going on inside this star. Let's look at this star right here and this little tiny core. We zoom in on the core. We have double fusion. So first there's the helium core that's fusing into carbon. Then surrounding it is the shell of hydrogen that's fusing into helium. So it's giving off a lot of energy, and it's giving off tremendous radiation pressure that is pushing out and making this, keeping it as a large giant star. This is an HR diagram of a globular cluster that shows low mass stars in several different life stages. And so here we have the main sequence, and there's the main sequence turn-off point. And you learned in chapter 15 about the usefulness of that main sequence turn-off point, where there are no O stars, B stars, and A stars on the main sequence, which shows that they have died off. They've become other things. But here we're looking at the subgiants and the red giants. And this particular branch is the helium core fusion stars. So particularly right here is stars that are actually fusing helium into carbon. Eventually, a low mass star dies. Now, it has already finished what we call its lifetime. That doesn't mean it's died, because it's still a star. So remember, lifetime of a star, when we use that word, we're referring to its time on the main sequence. And in the past few minutes, I've been describing to you after it leaves the main sequence, when it's a subgiant and then a giant. Now we're going to look at the final stages where it ceases to be a star, where nuclear fusion will stop entirely. This picture is of the Helix Nebula, and it is the expanding outer layers of what used to be a star. And right at the middle, you can see a small white dot right there. And that is called a white dwarf. It's the leftover core of the star. Let's talk now about the double shell burning phase. After the core helium fusion stops, the helium fuses into carbon in a shell around the carbon core, and the hydrogen fused to helium in a shell around the helium layer. So remember, the core, when it was a main sequence star, it was hydrogen fusing into helium. Then it became an inert helium core, and then it started fusing helium into carbon. And eventually, all that helium turns into carbon, and you've got 2 shells around it fusing. So this double shell burning stage never reaches equilibrium. The fusion rate periodically spikes upward in a series of thermal pulses. And with each spike, convection dredges carbon up from the core and transports it to the surface. This is what happens with a star similar to our sun. It starts on the main sequence, and it goes up, and it becomes a subgiant. So we have right here, the down and to the right, the core of a subgiant going into a red giant, inert helium with a hydrogen fusing shell. And then it zigs and zags, and it gets to about right here, and we have helium fusing into carbon with a hydrogen fusing shell around it, and that's shown in this middle diagram. Then it zigs up again, and eventually all of that helium in the core has turned into carbon, so we have an inert carbon core with helium fusion in a shell, with hydrogen fusion in a shell around that. So that's double shell fusion. Now, it gets to a point where there's not going to be any more nuclear fusion in that core because it just cannot get hot enough to fuse carbon into the next higher elements. And so it just stops. There is still the fusion in the shells, and eventually what happens is the fusion in those shells pushes the outer layers of the star outward. So we have what's called a planetary nebula. And this is just the outer layers that float outward, leaving behind the core, the inert carbon core. In the case of the very lowest mass stars, sometimes it didn't even make it to carbon, sometimes it's just helium. But whatever it's made of, whether helium or carbon, it is the core that no longer has fusion. So now we can say that as a star, it has died because there's no fusion. Now, it is still very hot and very bright, just like an ember from a fire. Might not be any fire anymore, but still, it's a very hot piece of material, and it's got to cool off. So let's look at it as it goes down the Hertzsprung-Russell diagram, down and to the left. Think what that means going to the left. It's actually getting hotter. Now that sounds weird, that a star that is dead, as time goes by, actually gets hotter. Where is it getting that heat from? What's happening is that the outer layers of the star are floating away and they are revealing the hot center of the star. And so not that any heat is being generated, but rather the surface of the star is what used to be the interior of the star. It's just very hot. Well, eventually all the outer layers have floated away, and so it's going to start getting cooler and cooler. All the way it's getting dimmer and dimmer and dimmer, and it settles here in this region called white dwarfs. Now these white dwarfs, eventually they cool off and they will become yellow dwarfs, orange, red. They're going to cool off and go down below the Hertzsprung-Russell diagram. They'll eventually become black dwarfs. I say eventually because the universe has not existed long enough for any stars to cool off from being white dwarfs. But given many, many, many more billions of years, white dwarfs are expected to cool off and go into yellow, orange, red, and then eventually black. But for now, we have a galaxy that has many white dwarfs in it. These outer layers that are drifting away, that are floating away, are what's called planetary nebulae. A planetary nebula is a cloud. Remember, that's what a nebula is. It's a cloud of either gas or dust, in this case, mostly gas. And it's called planetary, not that it has anything to do with planets, except when they were first seen in telescopes, they looked like circles, which is what planets look like. And so they're basically nebulae that looked like planets, and astronomers called them planetary nebulae. The double shell burning of a star ends with a pulse that ejects the hydrogen and helium into space as a planetary nebula. The core left behind becomes a white dwarf. And in this picture down below, this is what's called the Eskimo Nebula. You can see right at the center is a white dot. That's the white dwarf. So that is the leftover core of highly compressed, high temperature carbon. Fusion progresses no further in a low mass star because the core temperature never grows hot enough for fusion of heavier elements. Some helium fuses to carbon to make oxygen, but for the most part, not too much of that happens. Degeneracy pressure supports the white dwarf against gravity. Degeneracy pressure, that's a word from quantum mechanics, and what it means is that the electrons are pushed against each other so much that they exert a pressure against each other and they hold this thing up against gravity. Let's think about how this relates to the sun. And let's think about how that relates to Earth. What is Earth's fate? Here is a timeline as we go from zero, when the sun was zero age in billions of years, and it's about 5 billion years old now, and then 10, and let's see what's going to happen. The sun is very gradually, right now, over the billions of years, very gradually growing in luminosity as it burns through its fuel. But it's going to get to a point when the sun is about 12.1 billion years old, and that's in about maybe 6 or 7, something like that, billion years. It will rise to 1,000 times its current luminosity level. And so it's going to leave the main sequence, it's going to get brighter. And remember the Hertzsprung-Russell diagram. Leaving the main sequence, going up on the diagram means getting brighter. And it will get way too hot for life on Earth. There's going to be something called a helium flash. And this is what happens when the triple helium nuclei, when they fuse into carbon. So there will be a sudden very high brightening and then dimming down, and then a series of thermal pulses that will push out the outer layers of the sun to become a planetary nebula, and then it'll go down in luminosity and transition to be a white dwarf. Now, this is a similar chart, but not measuring the luminosity of the sun, but rather the size of the sun, the radius. So here we have now the sun is gradually going big, getting bigger over the billions of years, but it's a very stable star actually. When it leaves the main sequence, it'll grow, and with the helium flash, it'll suddenly get bigger and then fall back down. But notice, look at it right here, it's about 10 times its current radius, and then it'll go up. Notice this dotted line, this horizontal line. This is the present radius of Earth's orbit. So when it does the helium flash and those final thermal pulses, the sun is actually expected to be as large as the radius of Earth's orbit around the sun. So the sun would consume the planet Earth, just barely. This has been the life of a low mass star. In the next video, we'll look at the life of a high mass star. Have a great day.